Log on, tune in, find out. Another good idea from Cambridge.
Raphael Rouquier will continue his series of lectures on higher representations of the algebra.
Okay, thanks. So I'll go down the categorical ladder today and mostly discuss categories. So you want eventually representations, even vector spaces, but mostly categories. So starting with the Cartan matrix A, one can associate a two-category A, curly A with a double bar, which is over ring K. So it's linear in the sense that it has objects, which are weights. It has, should maybe we call that, objects of A, just weights, and one arrows are sums of sums of products of EIs, FIs, and the two arrows are more complicated, but they form K modules. And they are made of various things. So what I would like to explain is what is the representation theory? What does it mean to do representation theory starting with such a two category? So instead of acting on vector spaces, we're acting on categories. And so we'll start with a V, with a collection so a family of K-linear categories. So you can think, if you want, of abelian categories, or triangulated categories, or just additive categories with Helm spaces being K modules. And so in action, a two representation of A on this family of V lambdas. And sometimes I will say on the sum of V lambdas. So that's the terminology. So that is a two functor, and that's the last time I will use that terminology, from A to, let's say, R to the two category of K-linear categories with R of lambda equals V of lambda. Sorry, equals V lambda. So that's the definition, and it's just equivalent. It's kind of definition you would use abstractly. So now I would like to tell you what this means, so you can somehow forget about what the categorical meaning really is. I'm going to unravel what this data involves and what conditions that data should satisfy. Right. So what is a two functor? So concretely, this is the data of so we have those various categories. So first we have to specify one arrow. So we need to be given functors EI and FIs between these categories. So functors EI that will go from V lambda plus alpha I. So for every I, we have a functor from V lambda for every lambda. So that's taking the images of those guys. And now we have to look at images of two arrows. And there are quite a few in our category. So we need to be given also natural transformation of functors. So let's say I will call them morphisms. So we have these various functors EI, and we need a natural transformation small xi from EI to itself, and one tau ij going from the composition of the functor ei and the functor ej to composition the other way around. So that's most of the data. There was another part in the construction of A. We also actually took Fi as a right adjoint of Ei. That was how Fi was defined. And to do that is the same as requiring, as giving certain maps, units and co-units of adjunctions. So I'll put it like this. So we have maps Ei, epsilon I, sorry, going from, or maybe I should say, well, okay. We should give it, maybe I will put it as the last thing, adjunctions. So in the definition of A, Fi was given as a right dual to Ei. So in terms of categories, it means that we're given functors like this, and an adjunction of between Ei and Fi. So Fi is realized as a right adjoint to Ei. So in some sense, part of the data, you're only given Ei, and you could define Fi as a right adjoint. So this would be a condition that Ei has a right adjoint. So anyway, so that's the data, and it has two subject, two conditions, and the conditions are that xi tau ij's satisfy certain Hacker relations. So this is what was involved the first day to define those Hacker algebras, or on Tuesday in the definition of this monoidal category B. That's one part of the story. And then the other part was what I introduced yesterday, which is to get this category A, you the last step involves inverting certain maps. So you can define certain maps sigma ij when I is not j, and other maps rho s lambda, rho I lambda, sorry. And you now view those maps as morphisms between functors acting on your categories, and you need these maps, these transformations of functors, to be invertible. Okay, when you want to, you start with an algebra and you invert some element, a representation of such a localized algebra is the same as a representation of the original algebra, where the elements you have inverted are invertible in your representation. Okay, that's a functorial or universal problem point of view in localization. So it's the same here. So that's it. So that's the structure of that's what a two representation of A is. You have a collection of categories. So one for each weight. So you have if you want, you start with a big category, the sum of V lambdas, which has a decomposition into weight spaces. And you have functors going up and down. That would be some kind of classical data. It would be the classical point of view of categorification. Maybe you would add adjunction as a classical point of view, but the new inputs are those two morphisms and certain requirements here. Okay. So, so far, that's a fairly general class of two representations. And when you study representations of Kac-Moody algebra, complex semi-simple algebras, you should first restrict at a reasonable class. You want to put reasonable finiteness assumptions, and the typical one is local nilpotency. So here you can ask, we will say that, so you define, you say that the two representation is locally nilpotent. Sorry, is integrable. that's a definition, if EIs and FIs are locally nilpotent. So that means if you take an object M in some V lambda, then if you apply your functor EI, you go to V lambda plus alpha I. Then you apply it again, you get to V lambda plus 2 alpha I, etc. And eventually you should get 0. And same for Fi. So there's an obvious notion of local nilpotency, and that gives rise to a notion of integrability. And somehow the main point in the theory, first point maybe, is to study those two representations of these categories on linear categories which are integrable. And there is, if you ask a similar question for Kac-Moody algebras, there's a nice theory. You can classify simple representations, and then you have a nice decomposition theorems. And we'll see shortly that there is a similar theory in this categorical framework. So before doing that, I'm at a stage where I can now make the link with Joe Schwang's lectures from last week and tell you that this data, in the case of SL2, is indeed the same as the data of an SL2 categorification. So I will do that in a slightly more general setting than SL2, because it's, I think, quite a little more transparent, and it explains certain Hecker algebra isomorphisms of the types that Sasha Kleshev discussed last week. So, so we'll be focusing on type A now. So how do we produce type A stuff? Well, one way is to start with a field K and to take I a subset of K, let's say finite if you want. I mean, construction works in the infinite case as well. So what my claim is that there is a natural structure of quiver on such a set, and it's defined as follows. We have a quiver. Which is defined by with vertex set, the quiver gamma I. So vertices are given by the set I, and you put an edge, you put an arrow from I to I plus 1, if both, of course, are in I. Okay, that's a fairly trivial way to define a quiver. And the quiver you'll get is going to be the possible types, well, of connected components. Well, you can get certainly type, say, AN as a connected component. But if the field K has characteristic P, you can also get components of type AP minus 1, 2. So that's possible connected components. So type A stuff arises naturally here, and in some sense, I mean, if you start with classical algebraic objects in this two representation theory, it seems that you mostly get type A, and that's basically the way you get a quiver of type A. Okay, still use. Okay, so now a definition. So maybe a last thing I should say is that you can associate, there is an associated Kac-Moody algebra. G, and which I will denote by SL index I. I have a quiver, I can define a Cartan matrix, I can define a Kac-Moody algebra, and the connected components are of that type, so my algebra is going to be made of SLNs and SLN hat algebra, direct sum of such algebra. So it's over C. I want always algebras over C. When I think of Kac-Moody algebras, well, actually, it's really the Z form of the universal enveloping algebra or the quantum version that shows up. But no relation between the field K, that's the field, it's the same letter as, the same type of K as the K there, and the actual field on which this algebra lives, which should really be, say, C or even Z. This has to do with taking K zeros somewhere in the realization. Okay, so definition, an SL I categorification. Okay, maybe a last piece of data, space here, is that I will choose, let V be a K-linear abelian category, such that, so I want something good finiteness condition, so I will assume that endomorphism of simple objects are just one-dimensional, and that every object has a finite composition series. The first condition is more technical nature. The second one is really, you do want to put that type of finiteness assumption. So now I'm just restating last week's definition, which was done for SL2. I'm doing it a slightly more general case because it's somehow easier. It's more, fits better in the framework. Is the data of a pair of adjoint functors, an adjoint pair EF of exact functors so first you're given adjoint functors, then you're given endomorphisms capital X, an endomorphism of E, and capital T, an endomorphism of E square. So you compose the functor E with itself. Such that the following holds. Okay, so that's all. That's the only data that is required. Okay, okay. There are two versions. Maybe let me give. I don't have it. Probably won't have time to do both versions, so I'll do the easier version, which is I will also assume that there is a decomposition. Decomposition such that. So that decomposition, it's a weight space decomposition. So you could expect that out of somewhere we will have a Cartan subalgebra acting, and that we can recover the decomposition. But here I'm really working with a derived algebra, so it's for SLN hat things get a bit more tricky. So for SLN, you could forget about 3.
And F is still a root matrix of the corresponding material, no?
Exactly, exactly. So you have once you have a quiver, you have a Cartan matrix, you have and I'm thinking of the SL type. Yeah. Thanks. I am. Sorry?
Also X.
Yes, there are 2 X. I'm sorry about that. Yeah. At that point, I think it's too late to. This X as a normal sum E, I should change it. I should have thought of another notation for for my root datum. I shouldn't have used X. That's something I need to keep in mind next time. So the requirements are similar to the ones you've seen last week. So here I'm doing something a little more general than SL2. So it's a bit surprising that I need only one E and one F. So you have to think of this one E as a principal having to do with the principal SL2. So this capital E is actually the sum of all EIs. So in a Lie algebra, if you take the sum of all EIs, well, you do get something, but it's you can't get the individual EIs back. Okay. Now we have objects in a category. So we have capital E is going to arise as a sum of various EIs, but we have an endomorphism of this object E. And this decomposition of E as a sum of EIs is going to rise as the eigenspace or generalized eigenspace decomposition of E under the action of X. So this X here is going to be used to split E in eigenspaces.
But then F is, shouldn't be such as another element from a substitution.
No, exactly. Because I mean, if you take sum of EIs and sum of FIs, they don't give you an SL2 triple. So, I mean, the SL2 trick is really thinking of E, yeah. SL2 principal SL2 trick. F is just going to be the sum of FIs as well. E and both E and F are sum of FIs. Such that, alors, so the first thing is that you have to define first EI be the generalized I eigenspace of X acting on E. That's defined for any element in your field. Okay. You can think of algebras and the E being given by transferring by bimodule. So somewhere you have a bimodule, you have an endomorphism of that bimodule. You can look at the generalized eigenspace. And you can do the same for F, because X is an endomorphism of E. So by adjunction, that defines an endomorphism of F. And you can also take the similar definition. And now I can tell you what the conditions are. So we require condition. I'm sorry about the, I say such that, but at some point I need to introduce more notation. So the conditions are that first condition is that E is actually equal to the sum of EIs where I runs in the set I. So that set I of elements of K should be the set of eigenvalues of X, or at least should contain the set of eigenvalues of X. The second condition, which you saw last week for SL2, was to require that on the Grothendieck group of the category, we should have an action of the Kac-Moody algebra. So the class of EIs, classes of EIs define an action of SLI on K0 or complexified K0, as you like. Let's say C transfer Z K0V. So at the level of the Grothendieck group, we should check that the Lie algebra, the defining relations of our Kac-Moody algebra hold. And the last thing, the last two things actually, two things here. One thing is that F should be isomorphic to a left adjoint of E. So it's a slightly funny way to put it. It means that we don't want this isomorphism to be part of the data. It's just F should happen to be to be left adjoint. And the fourth part is that we should have Hacker relations, XT. So Hacker, degenerate affine Hacker relation. Which I don't know if I have in my notes. No, I don't, so I'm going to set that. So that means if you use x and t to define an action on e to the n, so you should have a map from the degenerate affine Hecke algebra associated with, let's say, h n bar to the endomorphism of e to the n, where the generator, say, xi of your degenerate affine Hecke algebra of Sn acts by this construction. So you act at the position I starting from the right on E, and Ti, the generator of your Hecke algebra, which really is a quadratic, I mean, it is an involution now. Ti square is 1, where in the degenerate affine Hecke, it should go to e to the thanks, n minus I. And now it's n minus I minus 1, t e to the I minus 1. So those should define a representation of the degenerate affine Hecke algebra. So that would really be here, be prescribing two conditions, that there is some braiding involving t, and that there is a relation between t and e. Just need two relations. Okay, so I have to be careful with what I erase at that point. That's still right now. Oh wait, I forget the compatibility. The compatibility of E with the V lambdas, with the decomposition. So if I need something similar to that. So I need EI of V lambda included in V lambda plus alpha I, and Fi of V lambda in V lambda minus alpha. So you have just basically a category, and you can even somehow forget about 3. In the SLN case, it's not necessary. So you have a decomposition of your functor E, which is induced by the action of X. And then you need to check that the EIs and the FIs that you obtain, thanks to this decomposition, do give you a representation of SL, corresponding SL, on the Grothendieck group. And then you have some adjunction to check, and the usual Hecke relations. So now the claim is that this structure is equivalent to that structure here. So that's the first theorem of the theory. So far, everything can be checked in a rather straightforward and quick way. And now this requires this result builds on the paper with Joshua. This work on SL2 plus continuation of that type of work. So lots of calculations involved. So what's the theorem is that SLI categorification on V. So I fix V. So here A is corresponding to, AZ. Say AZ. So that's A tensor over K Z. And this is using the quiver I. So my starting point is a finite subset of K. With this finite subset, I can define a quiver and the Cartan matrix. But when I have a quiver, I can define a specialization of my coefficient ring that defines this category. So I have two notions. When I have this set I can consider these two categories, which is associated with this Kac-Moody algebra, and I can look at its actions on V on one hand. On the other hand, I can look at SLI categorifications. And the two notions are equivalent. So here you have to be a little careful because I want a two representation on V viewed not just as an additive category, but viewed as an abelian category. So I should say exact, maybe. So I want the EIs and the FIs indeed to induce exact functors from V to V, okay, not just linear functors. So in other terms, I want really a two functor from that category the category of abelian categories with exact functors. And I'm sure I forgot something else. Yeah, I forgot that scalars should be k and not z. So I should make a further tensor product. So maybe it's better to do it here. So I can specialize from this coefficient ring to z and then from z to k. Okay, and now the theorem is correct as it's stated fully. So the two data are equivalent, and it's almost clear that you have the same amount of data. So the only thing that's a little tricky is what was mentioned yesterday, is the adjunction. Oh no, wait, it comes as a condition, so what is a bit tricky there? Actually not too much. Sorry? Sorry, so there are two parts, which are one thing. I mean, the data is basically the same. You see, in this setting here, you have EIs, you have X and T's. Well, here it's a little different. You're right. There is a morphism. You have not capital X and capital T, but small x and small tau. So the first point. So in the proof, somehow there are two. There's a first step, which is to relate that Eker degenerate affine Eker algebras of Sn, of the symmetry group Sn, is equivalent to, is isomorphic to the Eker algebra associated of the quiver gamma I. So you have a quiver, so I can define a Eker algebra, that explains the first day. And so there are explicit formulas telling you what is tau ij in terms of capital T and conversely, and same for capital X and small x. And these are the formulas these are the type of formulas that Sasha Kleshev, I think, gave last week. So that's one part. So it's just a change of generator, and in some sense, you could have used a different kind of generators here, used directly quiver generator. So that's not a very, that's a fairly easy point to address. Just generator and relations to check. So the second point, which is more serious, is there are 2 points which are problematic. Is that on one hand, here you assume this, you ask for this type of adjunction, which is not something you ask in this framework here. There's only an adjunction in one direction, whereas here you have in one direction, but you want also an adjunction in the other direction. So there's a problem there. You need so the two rep definition. So why is there an adjunction FIEI? So that's a really SL2 type problem, and that requires some study of that, but that cannot be solved directly. Somehow you have to introduce another 2 category in which you force this adjunction. So there's a candidate for this adjunction, for what the adjunction should be in terms of the data, and you can force you can define a new 2 category by further localization, in which there will be such an adjunction, and you can show that on integrable 2 representations, the 2 categories are the same 2 categories of 2 representations. So that needs to be addressed somehow at a later stage. This question, you have to study first an auxiliary category, and then there is the most obvious issue, which is that here we're asking that certain Lie algebra relations hold at the level of the Grothendieck group, whereas here, if you look, for example, at the relations involving relations of the type commutator of EI with an Fj, these are taken care of by asking that certain maps are invertible, so they hold at a more functorial level. And so you need to show that those relations hold, that those maps are invertible, if you know only that So more on K0, this consequence holds. That's a more, that's step 1, that would be step 2, and that's step 3, is if you start with 2 categorification, so Y are sigma ij and rho s lambda isomorphisms. So that part, the fact that rho s lambdas are isomorphisms, was something that was already handled in the paper with Zhou Shuang. And sigma ij, it's similar, slightly more annoying because you need to use 2. So it's, I should call that S, I should call that I. You need to use, it's not just SL2, you need some kind of rank 2 Kac-Moody algebra. But again, I mean, it's a usual trick that you can view, you can work with just one vertex I, think of that being an SL2 and the J as being an operator inside some kind of SL2 representation. So it's, you can reduce that problem of showing that the sigma ij's are isomorphisms in this SL categorification setting to some SL2 properties, and again use the tools with developed with Zhou Shuang. So anyway, so there is, yeah, so that this equivalence can be proven, yeah.
Is that equivalence only to integrable reps?
That, yeah, thanks, that's integrable exact. That's the whole product, of course. And I suppose that that means I have forgotten a condition here that 6 EIs and FIs are locally nilpotent. Which, well, maybe I can say it here. Define an integrable. It's enough to check it on K0. So you need a locally finite representation of your Kac-Moody algebra. For each SL2, it should be locally finite. Okay, thanks. Yeah, and I mean, I don't know in the non-integrable case. It might be true in the non-integrable case, but the proof uses integrability, uses locally finiteness. Okay, so I mean, this theorem is somehow says that you can't really construct examples. And with this definition, it's very difficult to construct examples, to check invertibility of these maps. It's the only way to check it on example somehow is to prove such a general theorem. So if you're given an example, it's just too hard to check invertibility. On the other hand, if you ask such a general question, you can reduce the question to somehow the case of irreducible representations or irreducible 2 representation. So you have a general problem somehow dealing with the representations of your Kac-Moody algebra. And if you're given a specific representation, it's just impossible to check. But if you think, well, I might try to prove it for all representations, then you might realize that you can reduce that problem to simple representations, in which case you can solve it. So there's a similar strategy here, which again was a key strategy for SL2. Okay, so the point of this equivalence is that indeed, whereas constructing examples here would be very, very difficult. I mean, there are no. It's hard to construct algebraic examples here. In this setting, it's much easier because this more difficult part, I mean, involves checking things at the level of K0, and that's something that's been done in many cases, just classical calculations. You have Hacker relations, which often come from some kind of Schur-Wald duality or some geometrical calculation. So it's all pretty straightforward. And now I would like to finish by saying a few things about those categories. What are 2 representations? What is the structure? And some of that's involved. To prove this theorem, you have to use what I'm going to say now as well. So if you, I mean, instead of thinking of Kac-Moody algebras, you can think of complex semi-simple algebras and of finite dimensional representations. Okay, it's good enough for what I will be saying now. Somehow the real difference, something happens there when, from now on, taking a symmetrizable or non-symmetrizable Kac-Moody algebra, there would be some subtleties, but between a symmetric or symmetrizable Cat-Moody and a finite dimensional semi-simple complex algebra. There's no difference in the theory. So we want now to construct simple two representations. So you need to use dominant weights. So as usual, we set x plus as a dominant weight. And in terms of the ordinary representations, say one representations, how do you proceed? You construct a Verma module first as an induced module. So you take the universal enveloping algebra and let's say, do we have a notation for that? No. Anyway, let's put it in a slightly loose way. So you take a one-dimensional representation for the Cartan subalgebra. So the HIs act there by lambda of HI. Then you let the EIs act by 0, and then you induce U of G. So that's generated by EIs, and H zeta. So H zeta acts by zeta scalar lambda, and EI acts by 0 on this complex line, and you induce this as a unique simple quotient. So for when lambda is in X plus. And the set of all L lambdas is a set of all simple, integrable. So integrable, I include weight decomposition by and so representations of say U of G. So I'll be quick on that. Just to explain the classical theory, just take an induced module. It has a unique simple quotient. This way you get your simple module. So we want just to copy this construction. And there's a first funny thing is that as I mentioned last time, when we move to this two categorical thing, we should remember that already at the one categorical level, we shouldn't deal with the enveloping algebra of G, but with this categorical version where you take objects being the weight. And that makes this Verma module a little bit more funny to define, because it's an algebra has a regular representation, or there's a natural action of U of G on itself by left multiplication. If you think of a category, it doesn't have a regular representation. If you think of categories acting on themselves, it doesn't make sense. It's a monadal category. What you want to do is take fix an element, an object in your category, and take that as a basis for your, as an initial vector for your representation. So if you think in terms of quiver representations, that's maybe something you're more familiar with. So let me do it. Explain the construction for two categories. So we fix lambda in X plus, and we want to define a two category which will play the role first only of U of G acting on itself. So we'll do that. So let's define R. Let's define okay, the curly V. So we define V mu to be the category of homomorphisms in A from, I have to get it right, from lambda to mu. So my claim is that this, as a structure, the set of V mu's is naturally a two representation of A. So, well, we have the decomposition, and now we need to give functors. So that's a category, and so we need, say, to define an EI from V mu to V mu plus alpha I. So V mu is the category lambda mu. This is the category lambda plus alpha I mu. Okay, I think it's lambda alpha mu plus alpha I, better like that. So there's an obvious way to go from here to here. So when you have when we are in our 2 category A, we want a functor from here to here. Well, whenever we have an object EI, if we have a 1 arrow going from lambda to mu, we can compose it with EI, and we'll get a 1 arrow from lambda to mu plus alpha I. And by definition of 2 categories, this is going to be functorial. So that takes, say, a 1 arrow, f from lambda, let's say, L from lambda to mu. We map that to the composition with EI. So EI composed with L from lambda to mu plus alpha I. So in our 2 category, we can compose 1 arrows, and that's what we do. So that's, and you do something similar for FIs, etc. So that is a canonical way to endo this data with a structure of 2 representations. In some sense, that's 2 regular representation of A at lambda. If you think of the category associated to the algebra G, curly U of G of Wednesday, and if you try to define some kind of regular representation of that, you'll see that you can do that as soon as you pick up some object of your category, some weight lambda. Okay, so we have something that's not a vermamonius, that's the analog of just U of G. It's just that we have taken some kind of idempotent completion of our enveloping algebra. And so we have to multiply by some idempotent to get an integrable, to get just a weight module. And of course, this guy is not going to be integrable. I mean, the EIs are not locally nilpotent in the 2 category A, and so they won't be either in V. Here. So it's not integrable. So we are at that level. We have constructed a version of U of G, depending on the lambda. Now we need to factor out certain elements. We need to factor out the EIs. We have if we think of C lambda being C times a vector, highest weight vector, we need to say that the EIs act by 0 on them. And that's obtained by taking some sub-representation. Inside U of G, we take U of G times, inside a U of G times V lambda, we take U of G times EI times V lambda, the sum of those, and we kill that subspace. That's how we will get the induced module, delta of lambda. So here, we will define V prime mu to be the full subcategory of lambda mu with objects direct sums of objects of the form L times EI with L going from lambda plus alpha I to mu. You get a map from lambda to mu by first applying an EI and then a map like that. And so that's a full subcategory. And if I factor that out, it's the same as forcing EIs to act by 0 on lambda. So now we have the definition of a category that we'll call curly L of lambda. So it's defined by its mu part equal to V mu over V prime mu. So that means we have an additive category. We have an additive full subcategory. So the quotient means we keep the same object, and we send to 0 those maps of this category that factor out through an object of that category, the usual quotients of additive category. So working with additive category is much easier, or linear category is much easier than working with abelian or triangulated categories. Okay, so there is a reason why I call curly L and not whatever curly delta or so. is that this is already affording a simple representation. So proposition. So we have now L of lambda is a two representation of A. We can take its Grothendieck group as an additive category and tensor by C. And proposition is that L of lambda is isomorphic to C tensor over Z K0 L of lambda as representations of U of G. So the claim is that somehow what looks like a Verma type construction is already simple. And the reason why this is true, philosophical reason, is that we have that EI and FI are left and right adjoint. So somehow we have made a construction. We have made such an induced module, but at the same time we have forced the presence of a non-degenerate bilinear form on that module. And we know that if you take, I mean, you can endow this module delta of lambda with a bilinear form, which is G invariant, but that is degenerate. And if you kill the radical, you get precisely L of lambda. Somehow in this categorical construction, it's already built in. Yes? This is for general. Yeah. I should have said that. That's arbitrary. Thanks. Arbitrary Cartan matrix. Yeah, thanks.
And all of the checks that were meant to be very hard for.
I'm sorry?
And all the things that were meant to be very hard to check for representations are okay.
So somehow everything the only thing that's difficult is this. Well, that's long to prove. Is this theorem? I mean, all these things now are becoming easy again. So, but this theorem you prove later. I stated it early, but.
Well, I mean, because you said it when we branched to the theorem, it's easier to check the SLI categorification than say the isomorphism between all the maps.
Yeah.
The representation, true representation, it is easier to check all those isomorphisms.
Because it is defined as out of A. In A, it's enforced. Yes. Somehow you need to. So the proof of this theorem is by reduction somehow to those simple representations. So first you define those simple representations, then you have to study them in the case of SL2, because at the end it's really representation theory of SL2 that's crucial. So define simple two representations, study them for SL2, then you go back to proving that theorem. Okay, so the claim is that this holds, and a more concrete, I mean, when you want to write down the proof, an easy way is to say that there is actually a very nice result that tells you that, okay, L of lambda is a unique simple quotient, but you can give generators for the kernel, for the submodule. That's a classical result, which is quite nice. I'll record it now. And so L of lambda is delta of lambda modulo the submodule generated by EI to the power alpha HH lambda plus 1. Say 10 times this highest weight vector lambda. So this nice description. Okay. So to prove that's a curve small e. So to prove the proposition, basically you have to show that these things are zero, and that's an easy adjunction. So I don't know if I probably will skip it, but so for the proof of the proposition, I think in my notes I've switched lowest weight and highest weight at that point. So you want to show that endomorphisms, somewhere you have to evaluate endomorphisms in this category A. So you have to use some adjunction, which is that this is the same as homomorphisms from, so I need to move one Fi to the, so F is right adjoint, so I need, and the key point is that this, using the classical SL2 relations, you can break that. It's going to be EI to big power times Fi plus something involving a smaller power of EI. And anyway, you can use this decomposition of that to show that eventually this space is 0 when it acts on, so you get 0 on this representation L of lambda. I'm very sketchy here. I don't want to get into the details, but it's somewhere you use that this object is a direct summon of another object which acts by 0, and that's something that doesn't make sense in the decategorified setting. At the level of algebras, it's not because x plus y acts by 0 that x acts by 0, but on the other hand, if you have a category, if the sum of two objects is 0, then both of the objects are 0. So there's this trick, basically what you need in the proof, plus this adjunction. Not much more involved. Okay, so that was an attempt at giving a proof which was not very successful. But I should go on anyway. So there's the next step in representation theory. So once you have described simple representations in your category, is to try to break down objects as a sum of representations. So in the Kac-Moody case, if you take a reasonable category, then every, let's say, complex semi-simple algebra, finite dimensional representations, they are semi-simple. So I've told you what are the simple representations. And the next theorem that comes in the theory is that every representation is completely irreducible. So here, it can't be as nice because we're really working with the Z form of the enveloping algebra. Or if we could work in a graded setting, we would work with an integral quantum group, so it's not going to be a complete decomposition. So the best we can hope for are certain filtrations, and they do occur. And that's the next structure theorem. So we can classify some things that look like simple representations. And the next theorem is that every two representation is built out of such representations. So first theorem. So you take, so the first case of study is the isotypic case. If you take a representation whose character is a multiple of an irreducible character, or whose class in case 0 is a multiple of an irreducible representation, you would like to say that it's the representation itself is a multiple of that irreducible representation. So that's the first statement. So we take V, a two representation of A in the sense of linear categories, and we assume, let's assume that V is idempotent complete. So whenever you have an idempotent in an homomorphism ring of V, of an object of V, you can take, there is a corresponding decomposition of the object, and we assume that every object of V is a direct summand, say is in A times V. Okay, I will fix maybe a lambda in X plus now. Is in V lambda highest weight. So these are the objects, killed objects of V lambda killed by EI for I. So I take a representation and I assume that every object can be obtained by starting with an object in this category V lambda, which is killed by all EIs, and applying products of E's and F's. So that's the assumption. Then, so I will say that, I will call that maybe that V is lambda isotypic, is lambda generated, then there is an isomorphism or an equivalence of two representations. You can get V out of this category L of lambda by taking a certain tensor product over, say, the center. There are some technicalities here, but then I'll write a correct formula, but so too much detail. It's an isomorphism of two representations. Okay, so forget about maybe the complexities. I'm thinking of an isotypic case where the category V or its Grothendieck group is like a multiple of the simple representation with highest weight lambda. And then there's a structure theorem for that category V. It's obtained basically from this. There's this category L of lambda, which is unique depending only on lambda, and it's a multiple of that category. So multiple in the sense of categories. Well, in terms of representations, I would take my simple representation, and I would tensor by some vector space, which I can take to be the highest weight space. Okay, that's the structure of an isotypic representation. So now instead of the highest weight space, I take the highest weight category, and the tensor product is whatever it is, tensor product of additive categories. It's not so difficult to define. It's some kind of tensor product of algebras. And so the key point is that there is this multiplicity category, which is given by the highest weight space, which can be anything. You can put any category there, basically. And then you tensor over this well-defined unique category, and you get that's what your V is. So this highest weight space V lambda determines everything. So that's a very strong theorem that says in particular that if you look in the abelian setting, you can get a version of that theorem as well. If the K0 of V is isomorphic to the simple module L of lambda, that tells you that the category V is equivalent to L lambda up to some base change, basically. So there will be some local ring maybe here. So we have a very strong unicity theorem for categorifications of irreducible representations. And I will finish with the Jordan-Holder type theorem.
Sorry, what's the objects you get in that category A acting on V lambda highest weight?
So these are objects is a direct summand of.
Ah, right, okay.
Thanks. Thank you. Yeah. Thank you.
The multiplicity category is all of V lambda, not V lambda highest weight?
That's a consequence. I'm sorry. This implies V lambda equals V lambda highest weight. I'm sorry. Because things can't come from further down. I'm sorry. Yeah. I try to introduce a definition and use it at the same time. And collapse there. Definition is stupid in this case.
And what are the assumptions on the category V?
So it's just any K-linear category. So it's a general setting of two representations. So these theorems are much easier to prove so the more general the setting, some of the easier. So if you try to prove an abelian version, well, you better try to deduce it for that. And if you try to prove a triangulated version, then you're in lots of trouble. So it's, yeah. So I'm sorry? I'm sorry.
You don't have to see an integral. What comes out of this?
The
Integrable.
So integrable is also an assumption there. Probably. Let's put integrable. I'm sorry. I should have modified the definition and include integrable.
Will it not follow? On the direct sum of the highest weights.
Okay, I'm just how does the proof goes? No, I mean you could have a Verma module would be like that. So no. So integrability is not a consequence. So wait. No. You're right. No, you're right. It follows. Yeah. You're right. Yeah. By the way, it follows. from a trick similar to the proof. Yeah, it is automatically integrable because more going down and up is going to be a direct sum, so it's automatically integrable. Yeah, it's because of the don't degenerate exactly of that. Yeah, absolutely. Okay, so last thing is Jordan-Hölder. Answer 2. So what's the assumption? So you take a 2 representation, integrable, blah, blah, blah. So V, 2 representation. Maybe I put integrable because I don't remember. Consequence, idempotent complete. So. And I will assume that the weights don't go. If you want a complete reducibility theorem for Kac-Moody algebras, you have to be a bit careful, and that's the assumption I'll put there. I'll assume that the set of V lambdas, the set of lambdas, such that V lambda is non-zero, is bounded above. So, which means that if I take a sequence of weights such that V lambda is non-zero, that implies that the sequence is stationary. That's what I mean by bounded. So that's a classical assumption, classical condition to put on representation. I want to. So that means this whole thing is going. So there's going to be finitely many weights, which are lower bounds of all the weights for which V lambda is non-zero. So that's the assumption. Then, and the order, you say that lambda is less than lambda prime if lambda minus lambda prime is a non-negative linear combination of the alphas of the roots, simple roots. Okay, so now there exists a filtration. Finite filtration, 0 is V of 0, included in V of 1. Included in V of n equals V, such that V of I modulo V of L modulo V of L minus 1 is lambda L generated for some lambda L. Okay, I should really stop. So there is a filtration, which is not quite the filtration kind of Jordan-Hölder. Each slice is only an isotypic representation in that sense that it is of the type here. So that means you have a filtration compatible filtration by 2 sub-representations, and each slice itself is a multiple of this L of lambda. So there is not a complete decomposition theorem, but there is you can filter every such category V, and that's really one of the main points about 2 representations is that you can study certain categories V by doing them with actions of such a 2 category A, and because they have such extra structure, you can tell a lot about them. They will have a filtration, you can analyze successive quotients, etc. And if you're lucky enough that the K0 of V is irreducible, then you know exactly what your V is. So a number of equivalences in representation theory can be viewed as somehow 2 different categories realizing this same L of lambda. Okay, I'll stop there. Thanks.
So in the theorem in type A, you can convert 2 representations into SLI.
Yes.
Applications, is there any code or something like that on type A? Or the version of it? Okay.
So you can compare.
You type A, you can.
You want a non-type A version of that? Well, in some sense there is. I mean, there's one problem is that I don't know what to do with this starting with a subset of your field. So there might be a version for alpha and the algebras, but somehow you have to take eigenvalues of X should be irreducible representations of finite subgroup of SL2C, or there's something funny like that. I don't know how to make sense of that. But indeed, there is a version of that theorem in the sense that this key fact that it's enough to check relations on K0. This generalizes to other types. Yeah.
In this final theorem about a filtration, is there some order of the weights when you're taking these
Yes,
filtrations?
yes.
Okay. Is it going from bottom to up or top to bottom? Or?
I'm going to, yeah, one of the
One of them.
one or the other. I don't remember. Okay. You can ask the same question for representations of a Z of your Casimir algebra. One way, not the other.
I mean, couldn't you have the same lambda L appearing several times and they can appear in funny orders?
No, no. That you can put them all. The idea is that if you take lambda either minimal or maximal, I forget which of the two, then you can get all this proposition will generalize in the sense that you will get all the what comes from lambda of B. I mean, it will all come at once. You will have a fully faithful functor, and that's it. I mean, you all that part. So it cannot. There could exist filtrations which are in the wrong order, but you can always also write them in the right order. So it's a little bit bizarre. I'm not sure. I mean, that cannot happen with representations, but that can happen with this category. But category can be extension in one way or in another way, the same, without splitting or bizarre things.
So when you defined L of lambda over there, sorry, I'd forgotten whether the V sub u's were assumed to be additive or abelian.
Everything is additive.
Everything is
nothing
additive.
abelian.
You can
So if you
modify
want
it
the
categories.
abelian version of that, you should think of this as being modules over projective modules over some algebra. So you have to take just if you take representations of that category, it's going to give you an abelian category, and that will be the abelian categorification. If you take the homotopy category of that, you will get the triangulated categorification.
But can you show that this this subcategory is a Sayre subcategory that you can modify it, or?
Oh, it's I'm doing it at the additive level. So it's like if you take projective modules for an algebra, etc. So it's
Okay.
everything goes right. It's everything is easy with additive categories. So it will do what you're saying. If you pass to abelian categories, that will take one will be a Sayre subcategory.
So if there are no more questions, let's thank Raphael and all speakers this morning here.